please join me in welcoming our panel of speakers: Sarah Anthony, Rich Friedrich, Partush Manadhata, April Mitchell, and Julio Guijarro. So before we dive in, I'd like to take a minute to ask each of you to share with us what you're working on and how you're contributing and your teams are contributing to the machine.
Sure. My team is focused on creating the mechanical and thermal solutions for the machine. We translate the architectural and logical diagrams from the computer architects into physical systems, like the one you see here. We'll talk about that more in a minute.
Hi, my team's focused on system software for the machine. So we're responsible for operating systems, compilers, file systems, programming languages, programming models.
And our team is in charge of security. So we are building mechanisms both in hardware and software so that it's very difficult for bad guys, if not outright impossible, to either break into the machine, see your data, steal any of it, or destroy any of it.
And we are building applications that leverage this new architecture and demonstrating ways for you to harness your data like never before. We also want to seed the creative ecosystem through tools that will empower our developer community.
So my teams are responsible to work in the management of the machine to make it possible to do it at a scale in a simple way and accessible to almost everybody.
Great, thank you. And we wanted to share a little bit more with you about HP Labs and the machine because it's been such an ambitious and an important project for us. HP Labs is HP's central research organization, and we are passionate about making our research real. And as you've heard last year when you heard Martin Fink first announce the machine, it is an ambitious project. It's our most important research project. And we are really fundamentally reinventing the architecture of computing with the machine. And so the machine will enable computers to actually make a quantum leap in performance and efficiency. It's going to lower costs over the long term, and it's going to improve security. So what we'd like to do today is take a deeper look into the progress that we're making across every aspect of the machine and the architecture. And so these senior technologists are going to tell you a little bit more about the progress that they're making. So I wanted to start things off, and maybe April, you can start us off, just by kind of talking about some of the big challenges that our customers are facing, that our industry is facing, and how the machine is actually set to solve some of those big problems.
Absolutely. We all know that data is continuing to grow. Every revolution of every tire of every car is being recorded. Every step of every jogger, probably many of us here, is being tracked. And as that data grows exponentially, we realize that we're hitting the wall for how quickly we can process it. Moore's law has held for our entire lives, but we're approaching the point where we have so much data that we want to reason over at such a large scale that brute forcing it with processing power isn't going to be an option. So we want to rethink this new era of computing, one where we optimize for space instead of time. So let me give you an example. You all likely flew in on an airline to Las Vegas. Suppose you're getting ready for your departure flight, you're heading out, and you're there at the gate when the gate agent tells you that there's going to be a delay, there's been a malfunction, and they'll let you know how long it's going to be. Well, what's happening behind the scenes is that airline software system has kicked into overdrive. It is churning and churning, trying to find a recommended solution that optimizes first for the plane and where it is, then for the crew, and then if there's time and space available, maybe it will optimize for the passengers, usually not. What if we rethink this? Instead of trying to compute the answer in real time, what if we recall the ideal solution, one that we've considered from many more factors, an exploding space of factors such as the weather, maybe even passenger preferences, to deliver an ideal solution that gets you rerouted on that flight that leaves within the hour and is only 2 gates down? Wouldn't that be nice?
I think that would be amazing, but I really want to get a little more specific because how are we actually building these physical systems that can enable us to process all that data in real time? Because it sounds a little bit like a dream.
Sure, Martina. So looking at the visual here at the bottom, we're starting with the hardware. We're starting with the hardware stack there. And so we have the disaggregated system built on special purpose cores and large pools of non-volatile memory joined with photonic links. So those are the fundamental building blocks of the machine, the foundational technologies. However, we realize that we must identify an initial hardware platform and then build it to create the platform for the rest of that stack to prove their technologies upon. So here at Discover, we're really excited to share the details of those hardware plans, what that system looks like.
Mm-hmm.
So here I've brought a mechanical mock-up of our first node board. It has 3 main subsystems that compose the full board. First, we have up at the front end here, the memory fabric attached section. So when we talk about fabric attached memory, that's one of the key differentiating elements of the machine. It's really what creates that flattened memory hierarchy that changes the rest of the system stack as a result. So that's section 1. The subsection in the middle here is the computational subsection. So this is one SoC, and it's a directly attached and private memory. That's very different from the fabric attached memory here at the front. This SoC cannot directly access the fabric attached memory here. It must first get onto the fabric. So that brings us to the final and third subsystem at the back of the node, which is the local fabric switch. The SoC connects directly to the local fabric switch, as do the media controllers for the fabric attached memory at the front. So the SoC can go through this local fabric switch to then access this fabric attached memory, or it can go through the local fabric switch off node into our innovation zone board and connect back through to other nodes in the enclosure or to other nodes in the rack and access that fabric attached memory as if it were its own. All byte addressable memory space. So here in this one node volume, we have terabytes of memory, and we have hundreds of gigabits per second of bandwidth off the node. Now that's really important because we've really changed what I/O is. It's not I/O in the traditional sense. It's a memory pipe, similar to the pipe we have here embedded in the PCB, but it's connected off board now. It's got to be replicated at this large scale. And that's really where we get to needing photonics at the enclosure scale. So if you're interested in those details, I'd suggest you stop by the HP Pavilion and see the rest of the architecture in action, and we can talk through that in detail there.
I mean, when I hear, terabytes of memory, that sounds great. I mean, is that enough to just add a lot of memory? Is that going to be the answer to all of our prayers?
Well, so I think as Sarah has described, this revolutionary architecture is going to provide, I think, a great foundation for ultra-scale analytics, but it has a significant impact on the system software. If you think about it, the essential characteristics of the machine is that you have this massive capacity in terms of memory, as Sarah just described, but you also have tremendous bandwidth as well as very low latency. That's going to cause us to make modifications in the operating system and the software that sits on top of that.
So can you tell me a little bit more about how you're approaching the operating systems and the programming models differently?
Certainly. So when we look at the operating system, most of you know we're working on something we call Linux for the machine. And Linux has a different design center. In this architecture, there are no disk drives. So all of your memory is resident. And we're designing for a petabyte of non-volatile memory. So what's a petabyte? Yeah, that's a number that gets thrown around a lot. So that's 2 to the 50th bytes for those of you who like binary, or 10 to the 15th bytes for those of you who don't. But let me give you a visual example of a petabyte. If I said that this one lonely sheet of paper was a gigabyte, then it would take 1,000 sheets or two reams of paper to make a terabyte. And if I wanted a petabyte, I'd need 200 boxes of paper to make a petabyte. So it's one thing to program a system that can handle this much memory. It's something very different if there's 200 boxes, because they would fill the back of this stage. So our goal with the operating system is to look at memory management and virtual memory management on the scale of a petabyte. And so we've been doing some work there to understand those, how to best make those performance improvements. We're also working on some technology called Atlas, which you can see at the Hewlett-Packard Laboratory Pavilion on the show floor today. And that is some extensions to the C++ libraries that allow programmers to explicitly manage these persistent regions if they wish. We also have work around something called managed data structures, which is a Java-like environment that handles all that management for you so you don't have to. Finally, when we look at the data stores, the fact that you've gotten rid of disk drives means we can collapse the storage hierarchy. And therefore, we can see significant performance in things like file systems and key value stores. And we've created some highly scalable transaction management services that right now run about 20 to 50 times faster than typical key value systems on traditional server architectures.
So I don't know about all of you, but when I hear about these huge amounts of data that we'll be able to handle, I frankly think it's a little bit scary, because what's to stop the bad guys from getting access to all of that data? So Pratyush, I don't know, what are we going to do about this?
Well, of course, securing the machine is extremely difficult. Make no mistakes about it. But at the same time, I must tell you that it's very, very exciting to be a researcher and look at security, because we are doing things that are very unique and very different from what's in the past. For example, if you look at traditional systems, almost always security is an afterthought, right? We worry about building features, functionality, and then we bolt in security afterwards. With the machine, we are building security into the design. It's not an afterthought, it's a very conscious design decision. And these mechanisms, we're building them into all different layers of the machine. We're building them in the hardware, building them in the firmware, in the operating system, and also in the user space. But more than that, the mechanisms that are in the upper layer, they're protected by what's under them. So it'll be very difficult, if not impossible, it'll be extremely difficult for bad guys to get around that. So these are unique features that we bring in that people haven't done before. And the way we think about these mechanisms is following a framework that we call protect, detect, and recover. Mm-hmm. By protect, we will try our best to prevent bad things from happening in the first place. We will protect the nice kernel that Rich team is building. We have mechanisms to protect your data end to end while they're at rest on the fabric and while they're being used. We have isolation mechanisms so that nobody gets to your data unless you explicitly authorize that, not even the administrator of the machine. Right? So we're doing our best there. But at the same time, we recognize that some of these mechanisms would fail once in a while. Right? The bad guys would break in. That's the nature of the beast. So how fast can we detect that? And we have a number of mechanisms to do that. Well, let me point out one key difference from what's done in the past. Now, most of the detection, in fact, all the detection mechanisms we have today, they're in the same layer where the malware is. So it's very easy for the bad guys to get around the mechanisms we have in place. So what we do in the machine is that all the detection happens in a very secure world that's outside where the bad guys are in and can't be tampered with very, very easily. Right? So that guarantees, to the extent we can, that we will do detection very, very quickly. And once we do that, we will recover from that, so there is no permanent damage to your data. Right? So we are building mechanisms to recover the firmware, the kernel, also in the user space, so that your data is protected. Right. So just to recap, the reason you should feel confident about the machine is we try to prevent bad things from happening in the first place, but assuming that they do happen, we detect them and we recover from them. Right. And all these mechanisms, they are built to be very scalable, resilient, efficient in terms of time and power, and manageable. And speaking of manageability, I'm sure Julio would like to add something there.
Yeah, as you can imagine, management and security, they are very intimately connected. So security needs to be pushed in terms of the configuration. You need to have to use the management system to be able to secure the machine. But at the same time, the management of the machine has to be secure. So somebody gets to the management system, you could be exposing things that you don't want to, or the system ended up doing things that you don't want it to do. The other thing is that when you are doing the management of the system today, as Pratyush said, we are trying to protect even the data from the administrator's domain. So the administrators and the people that even own the machine, for example, in a cloud environment, they should never have access to anything more than what they need to do their job. They shouldn't have access to your data as a user or as a programmer. So the other thing that we are trying to do as well is looking into auditing and trust. You need to be able to trust those systems. You need to be able to see that when you are interacting with a physical system or a virtual system, that you are interacting with the right one. That is not a rogue system that is in place. And the final thing is what Pratyush was saying. When you detect that something wrong is going on in the machine or in the IT systems, you need to be able to take reaction measures against it. So if it is a failure, you need to be able to correct that failure and take something that allows you to recover. If it's an attack, you need to react to that attack in a manner that it is consistent with your policies. And you need to make sure that as well you understand the implications of taking those corrective measures. Because it could be that you are shutting down the main service in your system, and what you want to do is to effectively reduce the service while you correct it.
Well, and I mean, we're talking about massive scale systems here, right? When we talk about the machines. So at a certain point, how are we going to be able to ensure that people can actually keep up with those systems?
Yeah, so my team and I, we've been working more than a decade in large-scale systems. Starting with telecom systems, distributed systems for telecoms. Many years ago, then moving into utility computing for the scientific community, and in the last few years in cloud. All these systems have kind of the same feature. They have large scale. You're talking about thousands, in some instances, hundreds of thousands of systems that people have to manage. Today, if you look at the average of the industry, you have roughly 200 servers per admin. And these are dedicated admins for those systems. If you look at what is happening today, things like, for example, Moonshot, in just 6 racks, you get 12,000 servers, physical servers that you have to manage. That without taking into account the storage, the networking, the applications. So what we have been doing in labs is looking at the machine as a new opportunity to rethink and question everything that has been done before. So we are taking several approaches. One, the interaction that the human beings have with the machines, with the management systems. Looking at how that interaction happens through visualizations, but also using new devices, touch devices like tablets, for example. The second thing, we are taking advantage of the new kind of analytics, collaborating with people like April, sorry, about looking at the different types of analytics and taking advantage for them to apply to the management domain. And finally, reinventing completely how the automation systems works. Most of the automated systems that we have today, they scale to thousands of entities. If you go beyond that, anything based around workflows, scripting doesn't work. What you want is to move to declarative systems in which you tell the system what you want it to do for you, but you don't want to tell the system how it has to be done. So, and you want to see an early demonstration of this technology. We are showcasing in the HP Labs pavilion. We are showing how we are managing 12,000 of those systems running applications for Haven, in which we deploy IDOL and Hadoop, and one single person is managing all this through a single tablet. So, without having to have a specific domain about how all these different systems work.
You know, earlier when we were talking about how we're rethinking the operating systems and the programming models, it also made me wonder, how are we kind of rethinking our approach to analytics? And I know, April, this is something that your team is working a lot on.
Yes.
Can you share a little with us?
Yeah, it's an opportunity. We are rethinking how we solve problems, how we write algorithms, and we're beginning to program the way that we've always wanted to, where data is loaded into memory, it's accessible, and it's accessible at a much larger scale. Right now, there are only a few companies on the planet that can reason at such a large scale, and they do it through sheer compute power. When you have a petabyte of memory accessible within nanoseconds, that changes everything. We can bring these capabilities, these large-scale reasoning capabilities, to those who have the data, not just those who have the power.
Yeah. I mean, and Rich, did you want to add anything to that?
As April says, that's having that much memory gives you the opportunity to create a whole new set of analytics. And from a system software point of view, we want to make sure that we can provide data with very, very low latency, very high bandwidth. We also have to make sure that the data is reliable and protected. And you think about the new kinds of algorithms. About a decade ago, many of you probably remember when experimental economics kind of came into IT and we started using it for dynamic resource management in the data center and other things like that, right? That was a new algorithm that previously had not been seen in computer science. I think these systems are going to generate a whole new set of algorithms. We see that today with things like machine learning, right? Deep learning is a very trendy topic. The first neural net was built in 1964. There's nothing new there except today we have more massive computing power, which allows us to build deeper networks, and therefore they're now powerful. Imagine if they have this kind of memory, as April just mentioned. You can do these longitudinal studies. I think we'll see those new algorithms, and probably a set of algorithms that were abandoned 10 years ago or 15 years ago because there just wasn't enough resources available to run those kind of queries.
And Julio, I know that you and I have talked a lot about how the machine is actually even helping itself as well with those new analytics capabilities, right?
Yeah, so as I mentioned, we're taking advantage of new analytics applied to the domain of management. So the machine is for us in the research area, it's a very exciting new architecture. So as we've been mentioning here, most of the systems that we have today, they work around compute-centric. Everything is around the CPU, everything was about the processes and everything that we do. Today, data is key. And we are, this is probably the way I see it, the first generation that we are putting data at the center of it. So how do we take advantage? And when we do this kind of analytics for the machine in terms of management, we are taking advantage of that. So some of the stuff that we are not still talking about it, but is, as I said, we are demonstrating, for example, today how to use this to existing systems. But when you apply these new kinds of analytics to the new systems in which we can push this everywhere, we can push it from the silicon all the way to the software. Incredible things can be done. So, and also, one of the things that is really essential for management systems, when there is an attack, when there is a failure, time is key. So, and this new kind of analytics allows us to be able to react in a timely manner. So be as fast as we can. That is key. It's money, and it's also about how much data you could be leaking and losing in the system. So.
Right.
Well, to add to that, if you look at analytics today, customers are very worried about collecting and storing, processing sensitive data. And for good reasons too, right? Because we don't really know how to protect the data and give the guarantees that people would like to have. Now, if we deliver on our promise of security, if we are successful securing the machine the way we want, and I'm pretty sure we will be, then perhaps people will be much more comfortable storing and analyzing sensitive data, whether it's your health data or financial data. I don't know what it is, but I hope that people will be much more comfortable looking at those.
So we can imagine a space where we might see personal genomics really take off and become something that we can really get real value out of.
That's one area where we can have a very positive impact.
Absolutely. And so to talk about another example and go back to the one that we had at the beginning, April, when you were mentioning the airline example, how does the machine actually enable that? Is it just a faster way to process the data?
No, it's not just a faster way, it's really a better way to process the data, and it's approaching it from a different perspective. And we're really looking at the space-time trade-off to allow us to approach these problems in new ways. We're dealing with data the way we should, with it in memory, with it quickly accessible, and accessible at a much larger scale. And with that, we can really rethink this approach of how we go from data to insight, all the way to value in this new era of computing.
So I know that very often I ask the researchers a silly question, and if you've been to my presentations before, you'll know that I always ask them and they don't give me a straight answer, which is, I want to know, because I'm working with the researchers, when am I going to get my flying car? Everybody wants to know that, right? So what are we doing to really make things different in the future with transportation or with things like that?
I like that you asked that question, and so I'm prepared, because I knew you were going to ask for that flying car again. And I can give a bit of a teaser and say that we actually have a connected car demo that's running. And if you walk by the pavilion to see this demo, you can learn about a concept that we call distributed mesh computing. So what if we take the analytics and we take all of this reasoning we want to do and push it to the edge where the data is actually created? So you analyze the data at the edge. If I were a betting person, we're here in Las Vegas, and I would put my money on what could get us to that flying car, I think distributed mesh computing would be that answer.
Okay, so for those of you who want the same answer to my question, go ahead to the HP Labs Pavilion and check that out, distributed mesh computing. But I mean, in all seriousness, is it just about flying cars? I mean, or are we really trying to do something big here?
So I think it's fun to think about flying cars, and on my typical commute day in the Bay Area, I'd love to have a flying car most of the days. But I think the crucial thing is to think about what are we unlocking in terms of this, what I'd like to think of as an ultra-scale, real-time analytics platform. We've talked a little bit about it with the airline use case. You can also begin to think about personalized healthcare, right? So for the first time, you'd have access to data at your fingertips in a way that would allow you to determine what's the best course of action for a particular disease that you might have. Or imagine if we could begin to apply this in agriculture using things like distributed mesh computing, where we could maximize the food production with a minimum amount of water, which we know is scarce, and especially here in the western part of the US, and the minimum amount of pesticides and fertilizers. Or think about energy we live in a world where we're insatiable appetite for energy. How do we extract the hydrocarbons necessary to run the world, but do that in the most environmentally friendly way possible? And using things like the distributed mesh computing as well as the machine as the ultra-scale analytics platform, I think will allow us to tackle these kind of problems that the global challenges have that society faces today.
It's exciting, and I think it's important for all of you to know that we need everyone's help, I think, to make a difference in the world. So if you are interested in partnering with us, please, again, come and talk to us. We're all of the panelists are going to be available throughout Discover here in the HP Labs Pavilion. Come and see some examples of how we are actually making the machine research real. So we have proof points across all of the areas that our panelists discussed today. And if you would like to go deeper on any one of these topics in particular, we have a number of sessions throughout the event where you can actually hear from some of the panelists, go a little bit deeper, and learn more on some of the specifics about the machine, and bring us any questions that you have as well. So with that, maybe Livin, just take a moment to ask if anybody else has any closing thoughts that you'd like to share with the audience. And Julio, do you want to start?
Yeah, one thing that I would like to say, I emphasize, and you heard Petrus and April about the way we are using the machine for solving problems that are related to the machine. So in a way, we are using the machine to solve the problems that we have in management. But the same principles can be applied to other domains. We are on the research space, we are early adopters, and we are the people that started to think about how we do this. But there is nothing that stops you in your own domain to start thinking how you're going to use these kind of new systems that are data-centric, that they have large scale, that potentially they will be simple to use. So to exploit and to get some kind of advantage for your business. But you need to start thinking about it now, because this thing is coming. It's real. So it's not something that is going to happen in 10 years.
Absolutely.
Just to add to that and what Rich and April has been saying, one big advantage of this is privacy that we didn't talk about. The mechanisms we are building, especially in the DMC setting, gives you full control over your data. You don't have to send your data to a central location in the cloud or wherever that is that you don't trust. You get the same value that you get today, but your data is with you. You send only the relevant data. If you want treatment, then you send that part of your healthcare data that's relevant to that diagnosis. So you have full control over your data, and I think that's a big, big thing that we're going to provide to people going forward.
That's really exciting. I think privacy is something that everyone is really concerned about today. It's exciting to hear that we have a really different and tangible approach to making a difference there, right? Rich or Sarah, did you have any closing comments?
I'm good.
I guess I would just add that I would encourage everyone to come by and particularly endeavor to discuss with people the topics that you're not familiar with. We take that opportunity when we're here, both with the business units but also across our pavilion. And so if there's an area that just doesn't quite make sense, walk up to the researcher that's staffing the station and see if you can get to the point where you really get it, because it can be a really good light bulb moment with all of the tangible demonstrations that we have to offer.
And we are highlighting technologies from across all of these areas at the HP Labs Pavilion. So please come by. We'd love to have as technically deep conversation as you'd like today or tomorrow.
And we're just representing a few of the people that are behind the scenes and back home, and it's really exciting to be here and have the chance to talk with you about this new frontier that we're embarking on. It's a really exciting time to be part of HP.
I want to just ask everyone to please help me thank our panelists for taking the time to share with all of us the progress on the machine. Thank you so much. And if you have any further questions, we are all available to you throughout Discover. And thank you so much for coming to learn more about the machine.
Thank you.
Thank you.